this section is about rational exponents. Whenever you see the word rational, they're talking about fractions, okay? So we're going to have powers that are fractions, and then we have to understand what that means, okay? It doesn't quite mean what you think either, my guess is. And so this is really important, this first part, making sure that we understand how to follow the formula or the structure of it. So, notice over here, I have my formula, b to the x over y, so some fraction. That equates to the y being the index for a radical, and the x being the power on that b underneath the radical. Okay? And so what we're going to do for these first three, so I've got the square root of 25, the cube root of 27, and the fourth root of 81, we're going to rewrite these as a rational exponent. And we're going to walk through that whole process. If we follow this, that the index corresponds to the denominator of the power, of that fractional power. So in this case, what's the index? 2. So that's going to be the denominator. What's the index here? 3, and the index here is 4. So essentially we start, now I wrote the 2 in just so we're clear. So this means 25 to some fractional power with the denominator is 2. For this one, 27 with the denominator is 3, and 81 with the denominator is 4. Okay? Now the next part is figuring out the numerator of that fraction. And since that's the power on the number on the inside, well, what is the power on 25? 1. What's the power on 27? 1. And the power on 28? 1. So we can think about all of those as being raised to the first power, which makes the numerator of those fractions 1s. So in reality, what I have, 25 to the 1/2 power is equivalent to the square root of 25. 27 to the 1/3 power is equivalent to the cube root of 27, and 81 to the 1/4 power is equivalent to the 4th root of 81. So one of the confusions that people have sometimes is they think you take half of 25, or a third of 27, or a fourth of 81. That is not what an exponent, a fractional exponent means. Okay, it actually relates to radicals. Okay. And we're going to go through a bunch of examples and play around with some of the power rules and those kinds of things with the fractions and kind of go from there. I'm also going to show you a different version of this that I think is actually a little bit more useful, and we'll go through all that. Are there any questions before we move on to the first example?
No.
Okay. Here's the first one. So all you need to do is convert this. This is x to the 1/6, and convert it into radical form. Obviously, this is rational exponent form, so just rewrite it in radical form. Well, again, if you remember, the denominator is the index, okay? So that becomes the 6th root of x. You could put the 1 as x to the first, but you don't have to. How many had that, right? Okay, so in some of your problems, it's just going to ask you to do that. Convert it into radical form. Or it's going to have a radical and say, convert into rational exponents. So you have to know how to go in between both. The other kinds of problems you're going to see are ones like this, where it says evaluate. And so evaluate means we're actually going to find an answer. Now, here's the thing I don't want you to do, because some of you will figure out a way to do this with your calculator. That's not the point. I need to see the work, okay? And there's actually another form that's usually more useful. So look over here. This is the one that was on the first slide. Sometimes, though, we can take and just take this exponent, the x, and slide it out. And the reason that we can do that is sometimes this number will get smaller, and we'll be dealing with smaller numbers to begin with. Oftentimes when we, in this case, square 8, then we start getting some numbers that can get kind of bigger that we don't want to have to do. Most of the time, to be perfectly honest, in an evaluation situation, this is the one that you're going to want to use. Now, it's okay to use this one. That's fine. You'll get the same answer, and I'm about to show you both forms to prove to you that you get the same answer. But go ahead and try to simplify that and see what you end up with. Okay. So the first one is using this formula here. So where I'm actually going to square the 8 first. or the second one, I'm going to actually take the cube root of 8 first. Okay? So you have options. You have options. Okay? If I square the 8, what do I get? 64. If I take the cube root of 8, what do I get? 2. So in either case, so on the top I've got the cube root of 64, which maybe you know what that is now, okay? But it's probably easier for you to do 2 squared, yeah? Okay. Either way I get 4 is my answer. Okay, how many had that? Okay, good. So do you see what I'm saying in terms of making the numbers smaller? Kind of makes your life easier, and like you can do 2 squared in your head pretty simply, okay? So that's the first example. Any questions on that? Yes.
So to get 2 squared, do I just figure out the square root of 8?
Cube root of 8, yes. So the cube root of 8 is 2, and that's where this 2 comes from.
Okay, and then I just bring over the exponent too?
Yep. Okay, let's look at another one. 16 to the 3/4. Try that one. Either way, again, either one of those forms that I just showed you. Let's try this one. You put it in either one of these forms, the 4th root of 16 or the 4th root of 16 to the 3rd. Now, what Kaylin did, which is what I liked, she broke 16 down, and she came up with all the factors of 16 and eventually got to this. Okay? Since there's 4 of them, and it's the 4th root, then she knew that this has to be 2 to the 3rd. Okay, so in other words, the 4th root of 16 is 2. So that's good. And then that makes it easier. 2 to the 3rd, you probably can do that in your head. Okay, on the other hand, 16 to the 3rd, you probably can't do in your head. And so you're in one of these 2 places. It's either 2 to the 3rd, or you're taking the 4th root of 4096, which I don't expect you to do by hand. This I would do with your calculator. However, this one makes it a little bit easier. Either case, you get 8 as your final answer. Okay, how many had that correct? Very good. Okay, so that's evaluation. There's 2 other kinds of problems that we need to look at, and it's relating our power rules. Okay, so our power rules are still going to be the same even if our powers are fractions. We still follow the same rules. So for example, this problem, this is a to the 2/7 times a to the 4/7. When I multiply with exponents that have the same base, what do you do with the powers? Add them. Okay, so in a case like this, so even if I had a case like this, x squared, so if you weren't sure, if you didn't remember, okay, and you maybe just make up a problem, right? This was just x to the 9th. And you guys know how to do that. You've already proven to me that you know how to do that, okay? So in this particular problem over here, it's no different, except I'm having to add fractions together. The bases are the same. So in reality, all I'm going to do is take 2/7 plus 4/7, which is what? 6/7. So my final answer is a to the 6/7. Now here's something important to keep in mind, okay? The directions in most of these problems will tell you what form to put the answer in. However, if they don't tell you, like in this problem, I didn't tell you what form I wanted it in. So what you want to do, generally speaking, is stay consistent. If the problem starts off with rational exponents, your answer should end up with rational exponents. If the problem starts off with radicals, then your answer should end up with radicals. You just want to stay consistent with the problem if it doesn't tell you. Obviously, in the first few examples that we did, it told you which form to put it in. But a lot of times it's not going to tell you what form. So just stay consistent with what's in the problem. Are there any questions on this one? All right, let's look at another example. So here I've got this crazy fractional exponent thing all raised to another power. And so in reality, this problem is like a problem like this. N to the 3rd to the 5th. Okay? When I have power to a power like this, what do I do with the powers? Multiply them. Okay? So powers in the sky, we multiply. The same thing is going to be true for this problem over here. Okay? I'm going to take x to the 2/5 times 1/2. Y to the 1/3, so the 1/3 times 1/2, and the 2/5 times a half. Okay? So here's what that's going to look like. There's my two parts. So in reality, I have actually two problems built into one. Okay. So what is 2/5 times 1/2?
1/5.
1/5. The 2's just cancel, right? What about 1/3 times 1/2?
1/6.
1/6. Multiply across the top, multiply across the bottom, and that's it. So x to the 1/5, y to the 1/6. We're just multiplying the powers when they're power to a power. Okay? That's it. Okay? So the point of these exercises is for you to apply those power rules that you already know. Except the powers are just going to happen to be fractions. Okay? What if it was, and I didn't give you one of these, but let's do one real quick. Let's make one up. Let's say I had z to the 1/2 divided by z to the 1/3. What would I do? Subtract, right? So it's the same thing. Same idea. When I have power divided by a power and the bases are the same, I just subtract the powers. So this really is z to the 1/2 minus 1/3. And then you'd have to figure that out. Does anybody know what 1/2 minus 1/3 is?
1/6. Oh no, I hit multiply.
1/2 minus 1/3.
Oh, I hate divide.
1/6.
Are you sure?
That's what it says.
It's only 1/6 too.
It told you. Well, let's confirm it. What's the common denominator going to be for 2 and 3? 6. So how would I convert 1/2 to something over 6?
Multiply by 3.
Multiply by 3, so what's on top?
3.
3/6. Okay. So yeah, this does equal z to the 1/6, which is interesting because 1/2 minus 1/3 is the same as 1/2 times 1/3. Anyway, when we get two problems like that with division and the bases are the same, we subtract the power. So our power rules are all the same, even if we have fractions. Okay.
What?
So do you know the reason why I make z's with the little line through them?
So they don't look like your 2's.
They don't. Look, if I made a z, so look at my 2. Here's an example. Here's my 2. If I took that line out, actually let's just take the line out. Let's see. It kind of looked like a 2.
Oh yeah, you're right.
So that's why I started doing that, because I realized my z's and 2's started looking the same. So